Hi everyone, it's Mrs. Meehan, and in this lesson you will be introduced to the first kinematics equation. Before we get to that, just a quick do now, scalar or vector. Last class we went over scalars versus vectors towards the very end, and I just want to make sure that you're clear on what a scalar is versus a vector. So take a moment and answer the questions that will pop up in the prompt, and then I will reveal the answers. Okay, so let's go over this. A quantity that indicates magnitude only is a scalar. So when you're only giving a number, that would be a scalar quantity. Whereas a quantity that indicates both a magnitude and direction would be a vector. So the key there is that you're also indicating direction, and that's what turns a quantity into a vector. So let's do a quick check here. 5 meters. I will just put scalar versus, or S versus V for scalar versus vector. 5 meters would be a scalar, since it is only a magnitude, versus 30 meters per second east is a magnitude and a direction, so that would be a vector. The same with 5 kilometers north, that would be a vector. 20 degrees Celsius, that is only a magnitude, so that is a scalar. 256 bytes, that is also a scalar, no direction indicated. And 4,000 calories is also a scalar. So what we're going to learn today is the first of the 3 kinematics equations we'll be using throughout this unit to help describe motion at constant acceleration. So the first equation is going to relate velocity versus time. That's the one we'll be talking about today. The other 2, which we won't see yet, it will be in future lessons. The second one will relate position versus time. And the third one kind of combines 1 and 2. And you'll notice there's no time referenced in this equation. So in instances where you'll have to solve for an unknown and no time is given, you can still do that using this equation. Now you'll notice we have V and A here that represents velocity and acceleration. So before we get to the first kinematics equation, we have to go over average and instantaneous velocity. So in the last lesson, the first lesson that we did for the unit, we talked about speed. Now there are some similarities between speed versus velocity, but there is a key difference. So take a moment to watch this video clip. Okay, so in the video clip, it mentioned velocity. The calculation for velocity is very similar to speed. However, the main difference is that velocity is a vector. So you're not just giving a magnitude, for example, meters per second. It's that magnitude plus a direction. Average velocity. Sometimes during an object's motion, its velocity will change. For example, if you're driving to the grocery store, there may be a highway where the car travels quickly, and there may be stop signs where the car's velocity is 0. The average velocity for the trip can be found by dividing the total displacement by the elapsed time. So V is representing velocity, your average velocity here. Remember, delta X would be change in displacement. So we're looking for the total change in displacement. Now recall that displacement is a vector quantity. It is your change in position relative to an origin. So this is a vector quantity. Time, on the other hand, is a scalar quantity. But since we have this vector quantity of displacement present, what you end up with is a vector quantity for velocity. So velocity is a vector. This is why the average velocity can be positive, negative, or zero, depending on the motion with respect to that origin, the starting point. Instantaneous velocity, on the other hand, is different from average velocity. The average velocity can't tell us the velocity at every moment in time. It's just the average for the entire trip. So continuing with our trip to the grocery store, when the car stops at a stop sign, we say that its instantaneous velocity is zero. So that is the velocity in that very moment. The instantaneous velocity is the velocity of an object at a very brief moment in time. So mathematically, you would say that the instantaneous velocity, it's still that total displacement, that change in displacement divided by elapsed time, but we're making time zero, or at least it's very close to zero. So when you write the equation, you're basically just saying that this is time, not necessarily change in time, just time. So this instantaneous velocity can also be positive, negative, or zero, depending on that motion. Okay, so next we're going to talk a little bit about acceleration. Acceleration is the rate of change of velocity. So previously, we just talked about velocity, which is the change in displacement over time. Acceleration is that change in velocity over time. So again, we have a vector divided by a scalar, so acceleration will also be a vector quantity. Breaking down the equation further, when you're looking for a change in something, remember you're going to subtract the final minus the original. So your final velocity minus the initial or original velocity, and we'll divide that by time. So since acceleration is a vector, we'll only be needing a sign, so positive or negative. You can have a positive or negative acceleration. Since we're only considering constant acceleration, there's no need to differentiate between average and instantaneous acceleration. So we're only going to be looking at acceleration as a constant. The units for acceleration can be derived by substituting the correct units into the right-hand side of the equations. So we have velocity here, the units being meters per second, time measured in seconds. By simplifying it, you end up with meters per second squared. Okay, let's take a moment to quiz yourself. Acceleration is the rate of change of d, velocity. The unit for velocity is b, meters per second, the same as speed, except remember velocity is a vector and you will be indicating direction. The metric unit for acceleration is c, meters per second squared. Kinematics equation 1. Velocity versus time. Let's take a look at how we derive the first kinematics equation for describing motion at constant acceleration. We now know that acceleration equals change in velocity over change in time. So since delta means change, we can actually substitute that change in a written out form. So the change in velocity is that final velocity minus initial velocity. And the same thing for time. The change in time is that final time minus initial time. But we're going to let initial time equal 0. So in this case, we can just write time. Once we do that, the equation is now acceleration equals final velocity minus initial velocity divided by time. Next, we want to start solving for v. So we want to cancel out this t. So we'll multiply by time on both sides, which will give us acceleration times time now equals velocity final minus velocity initial. We can swap the equation there for a moment, make this a little bit easier. We want to just isolate velocity final. So now we add my initial velocity on both sides. So we end up with the first kinematics equation of velocity equals initial velocity plus acceleration times time. So what this equation is telling us is that it's telling us how an object's velocity changes as a function of time. Let's try this out with a couple questions. So starting from rest, you accelerate at 4 meters per second squared for 6 seconds. What is your final velocity? Using the first kinematics equation, simply substitute in the values. So since we're starting from rest, our initial velocity here is going to be 0 meters per second. Added to the 4 meters per second square acceleration times 6 seconds, you end up with 24 meters per second, c. You have an initial velocity of -3 meters per second. You then experience an acceleration of 2.5 meters per second squared for 9 seconds. What is your final velocity? Again, just plug the values into the first kinematics equation, and you will end up with 19.5 or 19.5 meters per second. How much time does it take to accelerate from an initial velocity of 20 meters per second to a final velocity of 100 meters per second if your acceleration is 1.5 meters per second squared? So we know that the first kinematics equation, you're solving for final velocity. Your next step is to rearrange that equation before you start plugging in numbers. So once we do that, we end up with time equals the change in velocity here, so velocity final minus that initial velocity divided by acceleration. Once you plug in the numbers, you'll end up with 53 seconds. An object accelerates at a rate of 1.5 meters per second for 4 seconds until it reaches a velocity of 10 meters per second. What was its initial velocity? This time we are looking for the initial velocity. So we know this is the equation we're using. You must then rearrange it algebraically so that we are now solving for initial velocity. Once you do that, plug in the known values from the problem, and you'll end up with 4 meters per second. Your next step is to complete the classwork. There is a simulation that has been assigned on Google Classroom, Erwin and Ruthie. There are also chapter problems, number 13, D through F, and numbers 15 through 19 that go along with this lesson. For homework, your chapter problems that relate to this lesson is number 14, D through F, and 20 to 25, plus any leftover classwork.